Here are two tables. On the left, students and the department each one belongs to. On the right, each department and the building it sits in. Now ask a simple question. Which building is Asha in? Neither table can answer it alone. The left knows Asha is in CS. The right knows CS is in Turing. The answer lies across the gap between them. To bridge that gap, we glue matching rows together into one wider row. That gluing is the join, the operator that finally makes relational algebra useful. Let's see exactly how it works. Cast your mind back. The cross product, R times S, pairs every row of R with every row of S, all combinations, most of them nonsense. Then selection, sigma, keeps only the rows that satisfy a condition. Chain them, take the product, then select the pairs that actually belong together. And you've built a join. Written in one line, R bow tie sub theta S equals sigma sub theta of R times S. That bow tie is the join symbol. The little theta underneath is the matching condition. This single equation is the seed of everything that follows. The condition theta can be anything. Greater than, less than, not equal, several tests joined by, and for example, pair an employee with a department only when the employee's salary clears that department's minimum. But there's one special case we lean on constantly. When theta is pure equality. R dot A equals S dot B. That's called an equijoin. A join whose condition is nothing but equals. One thing to hold on to. Both a theta join and an equijoin keep every column from both tables. Even the two columns being compared stay side by side as twins. Remember that, because the next operator quietly changes it. Here is the operator you'll reach for most. The natural join, written as a plain bow tie with no condition at all. It does something clever automatically. It finds every column the two tables share by name. Look, both tables have a column literally named debt. So the natural join joins on debt all by itself. No condition needed. The shared name is the condition. Now it walks the rows. Asha is in CS. CS sits in Turing those match, so they merge. Ravi is in EEE. EE is in Volta. Merge. Maya, also CS, pairs with Turing again. And Kiran. Kiran is in ME, but there is no ME row in the department table. No match. So Kiran is simply dropped. Hold that thought. Here is the result. 3 rows, Asha in Turing, Ravi in Volta, Maya in Turing. Every column from both tables is here, and each row is now complete. But notice the crucial detail. The shared column, depth, appears exactly once, not twice. That's what makes it a natural join rather than a plain equijoin. It merges the matching columns into a single copy. The natural join threw Kiran away because Kiran's department had no building. That silent dropping of rows is called an inner join. And sometimes it loses data you wanted to keep. Outer joins fix that. They keep the lonely, unmatched rows anyway and fill the missing side with null, the marker for unknown. Left outer keeps every left row, right outer, every right row. Full outer keeps both sides. Watch the left outer join of the very same tables. The first 3 rows are identical to before. But now, Kiran survives, kept on the strength of the left table alone. And because there was no building for ME, that one cell is filled with null, unknown. So the choice is yours. An inner join for only complete matches, an outer join when the unmatched rows still matter. One more small operator, rename, the Greek letter row of employee, labeled M, hands you a second, identical copy of the table under a fresh name. Why would you ever want a copy? Because sometimes a table must be joined to itself. Take an employee table where each person stores their manager's ID. To pair each employee with their manager's name, you need to join employee to employee. But if both sides are called employee, the condition employee.manager equals employee.ed is hopelessly ambiguous. Which employee? Rename breaks the tie. Call the second copy M, and the condition becomes crisp. And out come the pairs. Asha's manager is Maya. Ravi's manager also Maya. Kiran's manager is Asha. Maya herself has no manager, so she leads no pair. A table joined to itself, made possible entirely by rename. The last operator is the subtle one, division. It answers questions with the words for all hidden inside. On the left, who is enrolled in which course? On the right, the courses that are required, C1 and C2. Enroll divided by required asks. Which students are enrolled in every single required course? Not some, every one. That's the for all, the universal quantifier. And division is the only operator that captures it directly. So let's check each student against both required courses. S1 has C1, C2, and C3. Both required courses present. S1 qualifies. S2 has exactly C1 and C2. Both required courses covered. S2 qualifies as well, but S3 has only C1, C2 is missing. Out. And S4 has C2 and C3, but not C1. Also out. Missing even one required course disqualifies you completely. So the answer is S1 and S2. The students who took all of the required courses. That's what division delivers in a single stroke. Division isn't magic. You can build it from pieces you already have. Take all the candidate students, projection of A, then cross them with the required courses, and subtract what's actually in a. That leaves the required pairs each student is missing. For our tables, the missing pairs point at S3 and S4. Subtract them from the full list, and you're left with S1 and S2. Exactly the answer we found by hand. The formula and the intuition agree. Now the real power. Individually, these operators are modest. Together, they compose into any question you like. Say we want the names of every student in the Turing building. Read this expression from the inside out. First, the natural join glues each student to their building, the table we built earlier. Then selection keeps only the rows where the building is Turing. And finally, projection pulls out just the name column, dropping everything else. Trace it through our data. Turing holds Asha and Maya, so the query returns Asha and Maya. Three tiny operators, chained, answered a genuine question. That composability is the whole point of relational algebra. Your turn. Here are two tables, EMP, with a department each person works in, and LOC, giving each department a city. Pause the video, take the natural join of EMP and LOC, and answer one thing. How many rows come out? Here's the reasoning. Both tables share the column depth, so we join on it. Tara is in sales, which is Pune. Om is in tech, which is Delhi. Ira is in sales too, Pune again. But Neil is in HR, and there's no HR city, so Neil drops out. So the natural join has three rows, Tara, Om, and Ira, each now tagged with a city, and the depth column kept just once. If you answered 3 and remembered Neil gets dropped, you've got joins cold. Trap 1. The biggest. The natural join silently drops rows with no match. If you needed those rows, you wanted an outer join instead. Trap 2. The natural join matches on every column the two tables share by name. One accidental shared name, say a stray ID, and it joins on that too, quietly ruining the result. Trap 3. The shared column. A natural join keeps a single copy of it. An equi-join keeps both. Get the schema right. Many questions hinge on it. Trap 4. Joining a table to itself without renaming. Both sides would share every name, and the condition turns ambiguous. Rename one copy first. And trap 5. Division is strictly for all, not for some. Miss a single required row, and that entity is out. Spotting a hidden every is the whole skill. Let's lock it all in. A join is a cross product followed by a selection. That one idea generates the rest. The natural join matches every shared column name and keeps a single copy of each. An outer join rescues the unmatched rows, padding the missing side with null. Rename gives you a fresh copy of a table, which is what makes a self-join possible. And division is your for all. The entities tied to every single row of the divisor. Master these 5, and you can express almost any question a database can answer.